Okay, so we have turbine, and we have an inlet, and you have an outlet. Okay, and the inlet condition, we know that is 650 kilopascal. We're going to make these numbers later on a variable, and the temperature and S equal 6.6235. Okay,
What it says?
S is the entropy, and the pressure is 600. Okay, that's the diagram right now. So if we go to our tables, and we would like to, first we need to know if it's a saturated or is superheated. So we go to a pressure table because we know pressure, and first of all we don't have 6500, so we will need to interpolate there, but we know that for both 6.32 is greater than the saturated vapor, so we know it's superheated. We save that one. We move to our superheated table, and again we don't have tables for 6500 megapascal, and the value of entropy is not in any of these tables, so we will need to perform a double interpolation, right? Here we're gonna need to interpolate between these two values, and then here between these two values, and then with these two values interpolate with 6.5. So it's a double interpolation. And if we are looking temperature and enthalpy, we need to do it 6 times. If we are doing also finding specific volume, 9 times. In order to avoid that, we use EES. And if I go to my equation window, I will set pressure 1 equals 6500, and I will say already kilopascal. S1 equals 6.6223, and I will say it's kilojoule per kilogram Kelvin.
That's a minus, right?
No, if I say F2, it recognizes that it's kilogram Kelvin. Okay? So now I'm gonna compute my H. And I can do it explicitly. H1 will be enthalpy. What is my fluid? Steam. What is the conditions? Enthalpy equal S1, pressure equal pressure 1. If I F2, I have my values. And I know that this is kilojoules per kilogram. But you may be thinking, well, how do I remember all those numbers, all those things? I don't have to remember. I have it in this tab, function info. So okay, I would like to have the thermophysical property of a real gas, and that real gas is steam. And what I like to have is now the volume. let's say the internal energy. Now, how many properties does this has for? 2. Because we know that we need 2 independent properties for each from the postulate of state. Yes.
It is steam because it's saturated.
No, steam and water works the same way. We know let me change that. Let me do this. This will be U1. I don't have temperature, but I have S equal S1 and pressure 1, okay? And I have it. To your question, let's say that I will copy this. Oh, this works exactly as in Word. I can just select it, Control C, Control V, and I will make this number U. If I put _1, that's a different variable, and I will use now water instead of steam. Press F2, and you can see that the values are exactly the same. Okay, it's just that at the beginning of the program the name was steam and it stays, and I usually use steam because you use it more for power plants, but you can use steam and water the same way. You notice that when I put the underscore, it puts you as a subscript, so it allows you to have a more nice of a program. Okay, so you can have that. Now you can see some value, right? Instead of having 3 or 6 we just say 6 interpolations now. And you have we are gonna do it maybe once or twice for each subject, and then we're gonna use EES. Because you're not here to learn how to interpolate, but to get some insight for all the changes. Let's say that I would like to change the pressure. If I would like to change the pressure, then to 600 to 6600, another 6 interpolations, and you are loose in the math, and you are so focused on the interpolation that you lose the big picture. Okay, so that's why we are using EES. Questions so far? No? Another good thing is that we said that it can solve not explicit situations, right? Not explicit equations. It also applies for the properties. Some of you will remember this. Let's say that I have this, and my efficiency, let me pause it a little bit. Okay. Okay, so I'm gonna introduce now this new problem, and this is 10 megapascal times convert from megapascal to kilopascal. My temperature 635, and this is okay. Enthalpy, it's okay. I will compute entropy. Okay, and I have my initial conditions. If I press F2, I have my units. That's okay. Check units. If I press, I would like to see my formatted windows. It shows me the conversion factor. Okay. Now I will say, what do I know from state 2? I know that S2 equals S1. That quality 2 is 95%. So I can compute H2S to be the enthalpy of steam with S equal S2 and pressure equals P2. I don't know P2. That's the unknown. And the unknown is here in the argument of the function, and still we'll solve it. Okay? H2A equals, I will copy this. And what I will change is quality equals quality 1. So I will put here quality 1 equals 0.95. Right? If I try to solve it, it will say that I am missing information. What I am missing is the isentropic efficiency of the compressor, right? But I have not related the isentropic with the enthalpies. So okay, that's the definition. But it's again, it's difficult to see if I type it right or wrong. So I go to plot, window, formatted windows, and say, okay, yeah, it's H1 minus H2 actual, H1 minus H2S, and that's my efficiency. So if I press here, it said you have 11 equations, you have 11 variables, you can solve the problem. If I press F2, oh my God. Oh, try setting limit to avoid this problem. It says the absolute pressure is negative or 0. So you can go to options, function info, no, options, default info, and you say, okay, the pressure, let's start with pressure, could not be as low as minus infinity, should be above that. So I will say that it will be above 1, and my guess value is 1. So press F2, it solves. Okay, let me press F2 again. Oh my God.
So it's easy to make mistakes.
Yeah, it's easy to make mistakes. P2 variable, infinity. Hold on. That's why I solved it in advance, so I don't have these mistakes. Oh, sorry. Let me change this to 0.97. Yeah, that was a mistake. Oh my God. Hold on. Oh, hold on. I know where the mistake is. We need temperature 1. And we said temperature 1 is 635. So this enthalpy is T equal T1. Okay, yes, done. Okay, my pressure 2 is 5.66. Okay, now there are some other functions and some other characteristics of EES that are very appealing or help you to understand your process or to document your reports. If we go to our tables, you remember that we have the dome, right? The diagram, this diagram, the TS diagram or the pH diagram for steam, right? So we can do that here too. What is that, yes? Diego? Huh?
The textbook.
The textbook. Okay, good. Okay. Is the 5th edition? The 8th? Okay. That's what I'm telling you. You distract me, you distract others. You can wait for that 10, right? Please. Okay, diagram. We can plot property plots. So I can create a pH diagram of steam. Okay? And I will include 635 just because I have that in the problem statement. And I have my pH diagram for steam. Now, it would be nice if I can plot my process here. Right now I just have the turbine, right? Point 1, point 2, it will be a line. But I can plot the whole cycle if I have all the points. So I'm going to show how to plot them. In order to plot them, I need to convert my variables from scalars to vector. So I will make what in EES it's called an array table. An array table, it's a little bit different notation. H1 equals H1. This second part says that enthalpy is the variable and have a number of, it's a vector. So I have 1, 2, 3, or 4, or whatever the number of values that vector can have. This time we'll have only 2 values, right? H1, and I will have H2A equal H2. I cannot add any subscript to the array table. And I will do the same for the pressure. Pressure 1 equals pressure 1. Pressure 2 equals pressure 2. Notice that I am mixing capital and small cases, and it will recognize the same as the same variable, and that I can put the array on the side, on the left side or on the right side, and it doesn't matter. If I press F2, again it solves, but now I have available this button that said array table, and if I open it, I have pressure 1 and 2, pressure 1 and 2, enthalpy 1 and 2. So now I can overplot these properties in the diagram. So I go to Windows, plot Windows, and I have 2 plots. Remember, you will have the optimization, and we have this pH. So I can overlay the plot and say, no, I don't want to use my parametric table. I want to use my array table. and in the x-axis will be enthalpy and pressure, just the same as I have it here. I will put an automatic update just in case I change something, and I will have a line with this, and I will have it red. Okay, so right now it's just a line, but you can do it for a cycle. In the homework you are asked to do it for a cycle. Okay, questions so far? Yes.
Sure, when you was computing P2,
Yeah.
why did you use H2A
Mm-hmm.
and H2S? What's the main difference between those two?
Okay, H2S, we are using an actual turbine. So the ideal turbine will be an isentropic one. The entropy at the inlet and the outlet will be the same. But in an actual turbine, you have some irreversibilities inside, and you have an increase in entropy. So a characteristic of or a measurement of how good that turbine is will be an isentropic efficiency. And the isentropic efficiency is defined by the ratio of the actual work divided by the isentropic work.
So if you give us the isentropic efficiency, we necessarily need to use HS or HA?
Yes, yes. Okay? Okay, we still have time. In the power plant that we are going to analyze, or some of the power plants, you may have 2 or 3 or 4 turbines. So imagine doing this, what we just did, for every turbine. Okay? A lot of typing. Then for the compressor, you have 2 compressors. Same thing. Then you have the pumps. Same thing. If you know that you are going to experience a number of components that you're going to be using over and over again, you can create a procedure. And that procedure will save you time. Okay? So right now we are going to create one procedure. And the only thing in procedures is that you need to put it at the beginning of the program. So I will say procedure, and I can put any name. I will say turbine, and then I open my arguments. I will say, what is the argument? In this case will be H in. I will name it this way. Will be P in and P out. And I will tell the efficiency, okay? And then I will have 2 outlets, 2 outputs. I will have the enthalpy out, and I will have, let me say this, actual, and I will have the work, the net work, the work of the turbine, sorry. So if I start the procedure, I would say H in, sorry, S in, and I will put this way to differentiate that this is inside the procedure, and let me put here underscore, so it doesn't think that is the sign function. It will be entropy of steam at pressure equal pressure in, and H equal H in. I'll put underscore on everything. Hold on.
What does the column mean between EFF and H out?
Okay, this column means that these are the arguments of the function of the procedure, and these are the outputs of the procedure. Okay. H in okay, so in this case I am computing the entropy at the inlet of the turbine. Then I will say I will compute the enthalpy out S, because I know that I can compute the enthalpy if I have an isentropic turbine. So will be S equal enthalpy steam comma P equal P out comma and S equal S in. Okay. Then I need to compute the relation between enthalpy and isentropic efficiency. The only problem is that with procedures they cannot be implicit, they have to be explicit. So if we know so I want to compute H2 actual
You should resume the Have you resumed the recording?
yeah, will be H in minus eta efficiency times H in minus H out S. If you notice, I am not using numbers because I don't know if my turbine will be in state 1 or state 2 or the inlet will be in state 8. That it will change if you have one numbering and you have another numbering. So I'm leaving it general. So I have now H out, that's one of my outputs, and I will compute the net work, the work of the turbine. And this is H in minus H out actual, and that's it. But I can remember how to finish a procedure, so I always have the help here, and I can call procedure. Okay, and I also always have something here that tells me to do no procedures internal. It said that you need to end with the word end. So I go here and I said n. Okay, so now I have this number, and I need H in I can have I have H in because I computed. I have P in and P out. I need I don't have P out, but I can do it. P out P2 equals 5, let's say, and I can raise this.
Shouldn't you have like a lower dash in the H columns?
Nope.
Lower dash 8. But
Where?
it's
Here?
gonna be no in the top part. It's gonna be different. there?
Oh yes. Good. If I see my window, my formatted window, say okay, you have a procedure that is called turbine. It have in bold. This is the definition. It is the end of turbine, and you have this data. So I can call now. Call turbine. And what is my H in? H1, right? We have 5 minutes. What is my P in? P1. What is my P P out? P2. And what is my efficiency? Eta C. Then colon. How do I want my H out to be named? H2A. And what is the work? I will set work. If I run it, you notice that we have work as a new variable because it was defined in the procedure. Okay? You have H2A because it was defined in the procedure. And now it becomes a variable in your program. So you can use that to work several times. But one more thing that it has is that the fluid can be a variable too. So I will modify the procedure a little bit, and I will say, I don't want this to be steam, because I know that I can work with 134A or 600 or Toluen. So I will create a general fluid. Okay? This says that it's my general fluid. And I have to put it in my argument as well. Right? Now, I have it here, and I said fs equals steam.
So do you have to put it there, or can you put it directly in the turbine?
No, you are putting outside the procedure because you want it to be general. Yes.
Right now, you have P1 at 10,000, but it's not part of the procedure.
It's not part of the procedure, no? The procedure will call P1.
But in the procedure, you have any variable assigned to P1. Should it
Yes,
be called
P
like
in. P in. The first number that it reads, I said P1.
It's in order, okay.
Yeah. Right? P1 is P in, is H in.
But
I
when
call
you
it here.
When you call it, you have to first state it. Like,
Yeah. In the procedure you stated.
It calls the inputs in vertical order,
I know you can have it in different order.
regardless of the name.
No, look. P1 is first, H1 is second, is third. And I have, in my procedure, I have H1 first and P1 second.
But P1 and P/N are different variables.
P1 is a global variable, it's a variable of your program. P in is an internal variable. I can call this several times. Let me show you. Let me take this out for a sec. Well, let me finish that. So now I have cold turbine. Okay,
I got it.
you got it? Okay.
but when you call it, do you have to write
The same order than the yes. Okay. I press F2 and I have the same solution, but now I have the ability to change the fluid. Right? I can use say the fluid is now 134A. Press F2, it will solve it. It's about limits, of course, but it will solve it. Okay? So you can create a library of procedures that you use, and then you just call them. Okay. I think that that's it. We can try to put the diagram, and I will do it just for one variable. Let's say that in this I will put the pressure. I will delete this and this, and say I would like this to be an input variable, and this input variable would be pressure. Okay. So this pressure right now, it has a value of 1000, and I would like to have an output variable, and this output variable will be work, and work will be here. Okay. In order for this to function, I need to put in my equation window the pressure as a comment. And now, in my diagram, I can put a calculator here, and then calculate. Oh, take this out, calculate, and solve it. So now,
Can you change the 10,000 directly in the diagram?
here in the diagram, yes, calculate. So that's very handy when you want to create a tool for someone else to use it, but you don't want him or her to mess with your program, right? For instance, we have